All right, let's dive in. We're about to pull back the curtain on a hidden force that, honestly, shapes pretty much everything in our modern world. It's this invisible connection that powers our cities, moves our cars, and organizes our lives in ways you've probably never even thought about. So, let's get into it. So, let's kick things off with a little puzzle. Think about it. A simple compass, for finding north, a credit card for tapping to pay, and a massive screaming roller coaster. What on earth could possibly link these three things together? I know, it sounds totally random, but I promise you, by the end of this, the answer is not only going to be clear, it's going to be everywhere you look. You see, the answer to that little puzzle lies in one single, incredibly powerful principle. It's one of the fundamental forces of nature that we've been slowly, piece by piece, learning to master over centuries, and it governs everything from the light we see to the data on our phones. And that principle is electromagnetism. Yeah, I know, the definition sounds a little dry, right? All about electric charges interacting, but don't let that fool you for a second. This isn't just some abstract concept from a physics textbook. It is, and I mean this literally, the engine driving our entire technological civilization. And figuring this all out? Well, it didn't happen overnight. I mean, this has been a long time coming. It all started way back with the ancient Greeks, who noticed that if you rubbed amber with fur, it would magically attract little bits of stuff. Fast forward 1,000 years or so, and sailors in China were using lodestones, natural magnets, to navigate the oceans. Then you've got Ben Franklin flying a kite in a storm to prove lightning was electricity, all the way up to Max Planck completely blowing our minds and opening the door to the quantum world. What a journey. Okay, so let's start with the part of electromagnetism that we can kind of feel. Magnetic fields. These are the invisible forces that can produce very real, very powerful effects, from pushing things away to pulling them closer, creating motion, and even bringing a speeding machine to a dead stop. Now, to really get this, you have to understand this one crucial difference. On one hand, you've got permanent magnets. Think of the magnet on your fridge. It's made of a special material, and its magnetic field is just on, all the time. But on the other hand, you have electromagnets, and these are the real game changers. They're basically just a coil of wire that only becomes a magnet when you run an electric current through it. Flip a switch, you've got a magnet. Flip it again, it's just a piece of wire. Being able to turn this force on and off, that's the key to everything. And check out how we use both of these. That compass from our opening question, that's a tiny permanent magnet, always trying to align with Earth's own giant magnetic field. But those massive cranes and scrapyards, those use powerful electromagnets. They switch them on to lift tons of steel, move it, and then switch them off to drop it. Maglev trains use this same on-off power to literally float above the tracks. And pretty much all of our digital data used to be stored on hard drives using billions of tiny magnetic particles. But hang on, this is where it gets really, really cool. So what happens when you move a conducting metal, say a sheet of copper, through a strong magnetic field? Well, the field actually creates these little swirling loops of electrical current inside the metal itself. They're called eddy currents. And get this, these currents create their own magnetic field that pushes back against the first one, creating a powerful drag force. And that drag force turns out to be an amazing brake. And there it is. That's the answer to the roller coaster part of our puzzle. To slow the car down at the end of the ride, big copper fins slide between rows of powerful magnets. The eddy currents create this incredibly strong braking force with zero physical contact. No friction, no squealing, no parts to wear out. It's an invisible brake made of pure physics. And it's the same tech used to stop the blade of a circular saw in an instant for safety. Okay, so we've seen how magnetic fields can push and pull. But electromagnetism isn't just a stationary force. It can travel. And when it travels, it creates waves. These waves, well, they open up a whole spectrum of mind-bending possibilities. And this is that spectrum. Now, the single most important thing to realize here is that every single thing on this list, from radio waves to microwaves, visible light, all the way to X-rays, it's all the exact same phenomenon. The only difference is the wavelength, or how much energy it's carrying. It's all just electromagnetic radiation. It's all light. So let's zoom in on the radio wave part of that spectrum. We use it for way more than just listening to music. Think about RFID. A reader sends out a radio signal that actually powers up a tiny passive tag, kind of like those security tags on clothes, and that tag then beams its unique ID number back to the reader. And there's the last piece of our puzzle, the credit card, or more accurately, the tap-to-pay card, which uses this very same technology to complete a transaction. And once you know what it is, you start seeing it everywhere. This tech is silently running the world around us. It's how Amazon tracks millions of packages in a warehouse, how libraries let you check out a whole stack of books at once, how toll roads charge your account without you even slowing down, and how stores prevent theft. It's this huge, invisible network of data, all just riding on simple radio waves. But the power of these waves goes way beyond just sending information. If you concentrate these radio waves, you can do some truly incredible things. In medicine, there's a procedure called radiofrequency ablation. Doctors use a tiny probe to deliver focused, high-energy radio waves that literally cook and destroy cancer cells with pinpoint accuracy. Just think about that. The same fundamental force that tracks a pair of genes is being used to save lives. It is absolutely remarkable. So far, we've been looking at pretty big stuff, right? Trains, cranes, radio antennas, but to really understand what electromagnetism is and to see where it's all going, we have to shrink down, way, way down. We have to go down the quantum rabbit hole where all the familiar rules of our world start to get very, very strange. And this is the idea that started it all. Back in 1900, Max Planck figured out that energy isn't some continuous, smooth flow like water from a faucet. No, it turns out energy comes in tiny, discrete little packets. He called them quanta. It's kind of like money. You can have $1 or $2, but you can't have $1.50. At the smallest scales, energy works the same way. It comes in chunks. Now, knowing that rule allows us to build some really wild things, like these quantum dots. These are basically man-made crystals that are so tiny, we're talking just a few dozen atoms across, that the electrons inside them get trapped. This is called quantum confinement, and it completely changes the rules of how they behave, forcing them to interact with light in very specific, predictable ways. So what's the payoff? Well, here it is. Because of those weird quantum rules, the color of light a quantum dot spits out depends entirely and precisely on its size. If you make the dot just a little bit bigger, it emits red light. Make it a little smaller, and you get blue light. This amazing precision lets us tune them to create absolutely perfect, pure colors. And that's why they're now being used to create the stunningly vibrant and super efficient QD LED screens on the latest TVs. That's quantum physics, right there in your living room. Wow. So we've gone from magnets to roller coasters, from radio waves to cancer treatments, and all the way down to quantum dots that power our TVs. Let's try to bring this all back together and really appreciate what this single unifying force means for all of us. And the impact of this force even ripples through our economy and our environment. Get this. A medium-sized sugarcane distillery can earn about $1 million a year just by selling its surplus electricity. How? By burning its waste product to create steam, which spins a turbine connected to a generator. A classic, beautiful application of electromagnetism, turning motion into electricity. It's a perfect example of how these principles are woven into the very fabric of our world. In the end, it really is all connected. The simple magnetism in a compass is born from the quantum spin of countless individual electrons. The light arriving from a star billions of light years away is the very same radiation that heats up your lunch in a microwave. From motors and medicine to computers and communication, it's all governed by a single, elegant, and beautiful set of physical laws. Which brings us to one final huge question. Over the last 2 centuries, we've gotten incredibly good at using the fields and waves of electromagnetism. But we are just, and I mean just, beginning to understand its true quantum nature. So you have to wonder, what's next? What new technologies, what new connections will we discover when we finally truly master the quantum world?